So welcome back. In today's lecture, I am going to talk about orthogonal projections and orthogonal subspaces. Okay. And in the previous class, we have already seen that how to define orthogonal or orthonormal basis, and we have also able to understand that how to fix the coordinate system once I select the basis. Okay. So if you see the orthogonality, that is the generalization of the perpendicularity. It means that if I will just talk about dot product, at that time we are talking about something is perpendicular if their dot product equal to 0. Okay, and after that obviously we have generalized the notion of dot product, that is called inner product. And if I talk about the inner product, and if the inner product of two vectors, now vector may be anything, okay, if that equal to 0, then I will tell that two vector is basically orthogonal to each other. Okay, now what basic thing we are going to do now, that we are going to investigate the orthogonal projection of a vector onto a subspace. Okay, so I have some kind of vector and I have some kind of subspace, and now what I am going to do, I am going to project that particular vector and I am going to see their orthogonal projection. Okay, and why this is very important, because one can see in this class only that an operation that plays a key role in the least square estimation means we have already deal with the parameter estimation problem, we have seen the basic parameter estimation problem, and at that time we have used the least square minimization, and it is possible to show that at that time we are doing the same thing, that we have some kind of vector and we are projecting that vector on some kind of subspace. Okay, so we have to solve some unknown quantity, but we are going to perform this kind of linear algebraic operation. Okay, similarly what happens, that suppose I have some kind of system. So one of the way to understand the dynamics of system, we are gathering the input and output data, and suppose if I have already some kind of knowledge that if input and output data of this form, then this is the mathematical model of system, means people has already information that if I have some kind of system and if system is of the first order, then how basically their input and output is related. If that is second order, then how their input and output is related. Okay, similar kind of information they have already saved in some software or some computer. Now what happens, that if you have some system and if you are going to perform some kind of input output based modeling, so always we have to do some kind of approximation, because exactly I cannot able to see the behavior, because what happens, most of the system their behavior is not exact due to some kind of noises, some kind of disturbance, and due to that reason always whatever input and output data we are getting, and even if our system is first order, they are not matching with first order, second order, then that is not matching with second order. And at that time we are going to see that how basically this particular operation, that is orthogonal projection of a vector on some subspace, that plays a role. Okay, second thing is that we are also going to develop some kind of concept in today's lecture, that how one can talk about the orthogonality for a pair of subspace. Okay, so in first place we have vectors, and after that suppose I have this kind of vector and I have some kind of subspace. and I am going to project this subspace, and I am going to see that of this vector on this particular subspace. So this is one kind of operation. Second class of operation, now I have subspace, two subspace, and I am going to project one subspace onto another subspace, and then we are going to talk about the orthogonality, concept of orthogonality. Okay, so let us first start that suppose I have some kind of vector and I am going to project that vector on some kind of subspace. Okay, so that is called orthogonal projection. Okay, so now before going to discuss orthogonal projection, now we have already well aware that I have two different kind of spaces. One is finite dimensional space, another is infinite dimensional space. What is meaning of finite dimensional space? That number of element in basis vector, if that is finite, then that is called finite dimensional space. Okay, and if that is infinite, then that is called infinite dimensional space. It means that suppose I have three dimensional space, so in order to represent three dimensional space, I need those kind of basis vector which has three linearly independent vector. Okay, so any three linearly independent vector can represent this finite dimensional space. Okay, suppose I have to represent some kind of function or functional. Functional means function of function. At that time, I need some kind of basis which has infinite many element. Okay, and during linearization, Taylor series linearization or linear approximation, you might have seen that suppose if you have to represent fx about x0, at that time what basically we are doing, we are writing first term as a fx0, and after that c1 I have to calculate, and after that we are telling that okay, second term is nothing but x minus x0. Similarly, c2 into x minus x0 square. So these are the bases. So first basis is 1, another is x minus x0, x minus x0 square, x minus x0 cube. So I have to go up to infinite number of terms. So whenever I am going to talk about orthogonal projection, so for simplicity, what I am going to assume that I have some kind of finite dimensional subspace. But you can able to extend this for infinite dimensional subspace by taking proper inner product space, because we already know that whenever you have function space, then how to define the inner product. Okay, but for simplicity of discussion, I am just going to talk about the finite dimensional space. So what I am assuming that suppose W is some kind of vector that is subset of this vector V. So I have some kind of space V vector space, and W is the subset of that vector space, and I am assuming that that is a finite dimensional subspace. That kind of assumption. So subspace, I have already told you that whenever we are talking about subspace, means subspace is somehow all property like vector space. Okay, and I am going to talk here real inner product space. One can also define complex inner product space, but in this course I am going to limit myself only on inner means real inner product space. Okay, where we are just dealing with real numbers. Okay, so now what basically we want to do, initially we want to view W as a subspace of Euclidean space V, and V is Rm. So what I am assuming that I have some kind of Euclidean space. Euclidean space, whenever we are talking about Euclidean space, at that time we are assuming that I have some kind of column vectors, and column vectors, each column vector is some kind of entry from the real number. Okay, that I have represented by R, and m dimensional means I have m tuples of the real number, and distance I can able to define just like 2 norm. Okay, or just by ordinary dot product you can tell. Okay, so that kind of things I have, but you can able to generalize here also. You can take any inner product space and do same kind of treatment. Okay, so but for simplicity I am assuming that I have just column vectors, and after that whatever norm I am defining that is by dot product. Okay, it means that distance, whatever distance I am going to define here, that is I am going to define using two norm. Okay, so now what is our definition? Definition is a vector z that actually belongs to V is said to be orthogonal to a subspace, and I have defined this subspace W, that is subset of V. Okay, so I have vector, again you can see that this vector in same space, and I have taken now some kind of subspace of same vector space. Okay, and if that is orthogonal, then to every vector in W, so this should satisfy for all W that belongs to W. Okay, so this kind of relation should satisfy. What I mean to say that if this vector Z, if I am telling that is orthogonal to subspace this, so now I have to check for all vectors. I can take any arbitrary vector from this subspace of vector space V, and at that time I have to check the dot product, is that dot product is 0 or not. If that is 0, then I can tell that this vector Z is the orthogonal to this subspace W. Okay, so now since if I am talking about some kind of subspace, and you know that inside any subspace I have infinite many vectors, so checking this relation is not a easy task for each and every vector, and due to that reason again I have to simplify my result. Okay, and how to simplify the result? You already know that using basis vector I can able to represent whole space. Okay, so if I will develop some kind of condition in terms of basis vector, then there is no need to check for each and every vector. Okay, you have to just check for the basis vector. Okay, so same kind of things I am going to do here. That idea is that you can first select basis vector, and all of you are already well aware that infinite many basis vector is possible for some subspace. Okay, so what you can do, you can select one basis vector of that finite dimensional space. If that is true for one set of basis vector, then that is true for any other set of basis vector also. Okay, so what I am assuming that W is subspace of the vector space V, and these are the bases of that subspace. It means that any element of this subspace I can able to represent using this vector W1, W2 up to Wn. I am assuming that this is n dimensional space. So dimension of this subspace is n dimensional. Okay, now what I am telling that Z is orthogonal to W if it orthogonal to every basis vector. Okay, so you have to just now check the dot product. So this result is a little bit easier. Now I do not have to worry about each and every vector. Okay, so in this way I can able to check that some vector is perpendicular or orthogonal. I have to talk about orthogonality because now I am talking in generalized sense. Okay, so that is orthogonal if dot product of the basis vector, this Wi is the basis vector, and z is some kind of vector that belongs to V. So this is actually orthogonal to this subspace if this relation will satisfy for all basis vector, and in n dimensional space, since I am assuming that whatever subspace their dimension is n, so n number of linearly independent vector is required to represent that space, and due to that reason I have to now just check n number of equality that equal to 0. Okay, if that is satisfied, then I can tell that okay, Z is now the orthogonal to this subspace W. Okay, and same kind of things I have written here. Indeed, any other vector in W can be represented like this, where C1, C2 is the coordinate system. In the previous class we have already seen that whenever I fix the basis vector, so basis vector is not unique, but once you fix it, then coordinate system is already unique. we know that how to find this C1, C2 and Cn. Okay, either you can go via orthogonal basis or orthonormal basis, you are able to find C1, C2, Cn very easily. Okay, and now what I am going to do, I am going to apply the linearity. By applying the linearity, since each and every vector is perpendicular, so I can tell that z and w are perpendicular, and due to that reason this requirement comes into picture. Okay, now I am going to talk about the second definition. So in first definition, what we have seen, that I have some kind of vector and I have to check that that vector is actually orthogonal to subspace or not. And how to check that? You can just actually identify the basis vector of that particular subspace, and after that take the inner product of that basis vector with that particular vector, and if that equal to 0, then I can give guarantee that actually that vector is orthogonal to some subspace, and that vector and subspace both are actually belongs to same space. Okay, now what I am telling, that the orthogonal projection of V onto the subspace W is the element that W, that is belongs to that subspace W, that makes the difference orthogonal to W. Okay, so this result or this definition is very important. Okay, now what I am telling, suppose that I have some kind of vector V and I have some kind of subspace W. Okay, and what I have to do, I have to project this vector V, okay, on this vector W. Okay, so if you do that projection, then what happens, that projection of V on W, at that time it is possible to show that V minus W, okay, that is nothing but that is Z, and that is orthogonal to the W. Okay, so from here you can see that I have V and I have to project this V on this particular subspace W. Okay, so if you project this, then obviously you will get some kind of vector on this particular subspace, and I have given name of that vector as a W. Okay, obviously W is going to lie on this particular subspace. Okay, so now if you see this vector I am going to project on this particular subspace, so it is possible to show that difference of these two, either you can tell like this or this, so that is perpendicular to this particular subspace. Okay, so that kind of, or orthogonal, I have to tell orthogonal because I am again talking about the inner product, orthogonal to the W. Okay, so in order to check orthogonality, that whatever projection of some vector here, so that is orthogonal or not, so just you have to check that Z is perpendicular to W or not. Okay, and here now I am going to state the theorem, and what this theorem is telling, that let u1, u2 and un be a orthonormal basis. Okay, so in the previous class I have already talked about orthogonal or orthonormal. Okay, so please check it carefully. Okay, that what is difference between orthogonal and orthonormal. Okay, so I am assuming that u1, u2 and un be a orthonormal basis of a subspace W, that is subset of vector space V. Then orthogonal projection of some vector V that actually belongs to V onto W is given by C1 U1, C2 U2 and Cn and Un, and it is possible to show that this coordinate C1, C2 and Cn I can able to calculate just by taking the inner product of this vector V, which I am going to project on the W subspace. So W, now what I have to do, I have to just identify the normal basis of the subspace W. So if I know the orthonormal basis of the subspace, then I can able to calculate the orthogonal projection of any vector on that particular subspace. So this result is suggesting that. Okay, so since this is the theorem, so we have to prove it. Okay, so now proof is not too difficult, since I am assuming that u1, u2 and un form a basis of subspace. So whenever they are forming the basis of subspace, so it is possible to show that any vector you can take. Okay, and that vector is nothing but the linear combination of this basis vector, and we know that u1, u2 and un, by the assumption of this theorem, that is normal basis. Okay, so orthonormal basis means if you take the norm of this, that is unity. Okay, so now first what I am going to do, I am going to express any vector of this subspace using C1 U1, C2 U2, Cn Un. Okay, now I have to identify C1 and Cn if this W is the orthogonal projection of that vector V. Okay, so due to that reason, now what I have to do, I have to apply the definition of orthogonal projection. Okay, and in previous definition, what we have seen that if I have some vector V, and if I have some subspace W, and if Z is the orthogonal, if I will tell that V is projected on some subspace W, okay, then what happens, that Z, that is difference between V and W, that is orthogonal to W. Okay, so same kind of things I am going to use here, because now I have to calculate the orthogonal projection. So due to that reason, what I am going to do, I am telling that Z, that is V minus W, that is orthogonal to W. Okay, and now using orthogonality assumption, I can tell that since Z is the orthogonal to subspace W, so if I take any vector of W, okay, and if I take the dot product or inner product of W with Z, then that equal to 0. Okay, because Z is the orthogonal to W, and due to that reason, and I have to check for each and every vector of W. I have already told you that another simplest way, you can just see the basis vector. Okay, and you can take the dot product of each and every basis vector that equal to 0. So same kind of result actually I have used here. What I am telling that Z is perpendicular to ui, and what I have done, I have selected actually ith basis element, and if Z is perpendicular to W, so that is perpendicular to basis element, so that I have substituted equal to 0. Okay, and in place of Z, now I have substituted V minus W by definition of the projection. Okay, and after that, now what you can do, you can just open the bracket by linearity, and it is possible to show that this V minus ui, and everywhere whenever they are the same at Ci, when ui into ui at that time, that is unity, all other place that is equal to 0. Okay, and from this result you can see that I can able to identify Ci. And what is Ci? Ci is now nothing but the inner product of V. So V I have to project on W, so inner product of V on ui, and in this way I can able to calculate the coordinate system C1 and C2. Okay, and same result I have actually stated here. Okay, so now result is very simple. Suppose you have some vector V, okay, and some subspace is given to you. Okay, so one of the most important work first you have to do, you have to identify the orthonormal basis of that particular subspace. Okay, and after that what you have to do, you have to write W vector projection vector in the linear combination of or orthonormal basis, and how to calculate the coordinate associated with each and every element. Now you can select V, and one by one you can select the basis element and take their inner product. Okay, a standard inner product, dot product you can take, or any other inner product, that is also completely fine. Okay, so in this way one can able to prove, and this is also unique because we have seen that Ci equal to given by this, so only one way I have, and due to that reason uniquely I can able to identify this coordinate. Okay, and more generally, suppose if you don't have orthonormal basis, so you can also go with orthonormal basis, but at that time just you have to divide by their magnitude. Okay, and you can take the norm, any two norm you can take. If you are considering the standard dot product, then two norm you can take, and after that you can, because corresponding to every inner product I have some specific norm. Okay, so once you are fixing the inner product, corresponding norm you have to take. Okay, so in this way, even if I have some kind of orthogonal basis, I can able to do that. Okay, I am able to express the projection of vector V on some subspace W. Okay, please be careful that V belongs to the whatever vector space, same W is the subspace of same vector space. That kind of assumption we have. Okay, now what I have to do, suppose I have some kind of plane, and plane I have defined W that belongs to R3, and that is spanned by the orthogonal vectors. Orthogonal vectors means if you take the dot product of these two vectors that equal to 0, you can check it. V1 and dot V2 standard dot product I have taken here, so inner product as a dot product I have taken here, that equal to 0. Now by using formula I can able to project this vector onto this vector. Okay, so what happens, you can see that I have just two vectors and I have to span the three-dimensional space. Okay, so what happens that I am only able to generate some two-dimensional space out of the three dimension. Okay, so I have two independent vector, and due to that reason, if I have V1 and V2, then I am only able to span some kind of subspace of three-dimensional vector space. Okay, so now what I have to do, I want to project this vector. So in three-dimensional space, suppose I have three vectors. So one standard basis is 1 0 0. Okay, and I want to project that standard vector on this particular subspace that is spanned by this orthogonal vector. Okay, so how to do that? Again, I can write W, and since V1 and V2 are orthogonal vector, so that is nothing but orthogonal basis. So orthogonal basis I have substituted here, and after that what I have to do, I have to project this vector on first orthogonal basis, and since this is not orthogonal, so due to that reason I have to take the corresponding norm. If you take the dot product, then two norm is okay. Okay, so two norm I have taken here, and in this way I can able to get the projection of this vector on that subspace that is generated by these two orthonormal vectors. Okay, now similar kind of things you can see that what you can do. First, you can convert orthogonal basis into orthonormal basis, and how to do that? Just you have to divide with magnitude. Okay, so you can take the norm and divide with the norm, then that orthogonal basis is converted into orthonormal basis. Okay, and after that now you can calculate the coordinate system V and inner product with U1, V with inner product with U2. It is possible to show that again you can get the same result. Okay, so in this part what basically we have seen that if I have some kind of vectors, okay, of some vector space V, and if I have some kind of subspace of same vector space V, then how to define the projection? Okay, so one can able to identify the projection vector using the help of the orthogonal or orthonormal basis of that particular subspace. Okay, now I can able to use this result now to interpret the least square estimation. Okay, so what I can do, first I will complete that part, and after that I will come to the orthogonal subspace. Okay, so in the previous class, okay, what we have seen, that suppose I have some kind of system, a static system I have considered, and after that what we have seen, that and that explanatory variable is phi. Okay, and I have some kind of unknown parameters. I have to estimate the parameter. So that kind of problem we have seen, and using the least square estimation method, what I will do the least square, then this kind of expression comes into picture. Okay, what does it mean? That exactly I cannot able to estimate this new. Okay, new is nothing but some kind of parameter. Okay, so what I am assuming here, that y belongs to Rn. Okay, and I am assuming that I have some kind of explanatory variable that belongs to Rp. Okay, so I have n number of information measurement and p number of explanatory variable. Okay, and now not p number of explanatory variable, you can take see that since I have to do this kind of means I have to interpret this, so I have n number of y, and after that I am assuming that I have v I am assuming that belongs to Rp. Okay, so I have p number of unknown. Okay, and correspondingly I can fix the phi. Okay, so since I am assuming this belongs to Rn, this belongs to Rp, so this is nothing but n cross p. Okay, so what I am assuming, that I have n number of sample and I have p number of unknowns. Okay, and I have to estimate that kind of unknown from that p number of measurement. Okay, so I have some kind of system and I will do some kind of experiment. Okay, and I will repeat that experiment for n time. Okay, and after that what I have done, each and every experiment I have actually recorded that output. Okay, in previous class we have seen that if I have that kind of recording, then how to get the mathematical model of some system. Okay, and at that time it is possible to show that exactly I cannot able to get this unknown new. Okay, and due to that reason I have written new cap, and new cap I can able to estimate like this. Okay, so if I have more number of unknowns, and at that time it is possible to show that more equation than unknown means more number of measurement than unknown, then I can able to get that unknown by solving this kind of pseudo inverse. This is called pseudo inverse. Okay, suppose that if I will do number of experiment that is less inverse is actually reduced to phi inverse y. It is possible to see here that if more times, it is possible to show you are able to get best estimation of that unknown. We have seen that using the help of pseudo inverse, I can able to estimate that unknown parameter. Okay, now I am going to regenerate again same result with the help of the orthogonal projection. Okay, so what we have seen now, that I have some kind of vectors, and if I have some kind of subspace, okay, so I can able to project that vector on that particular subspace, and at that time orthogonal projection one can define like this. Same thing I have actually defined here, zeta equal to a minus eta. Okay, and what kind of things that comes into picture, that this eta and zeta are perpendicular to each other, because eta is going to belongs on the direction of that subspace. Okay, so orthogonal projection, that is zeta, that is perpendicular to that. Okay, now what I am going to do, I have vector A, and I have to project that vector on this subspace. Suppose that subspace B in R2 two-dimensional space. Okay, so at that time again what I am going to do, I am going to take the A transpose A. At that time I can able to represent like this. Okay, so I have to project vector A on vector B. So I have taken the transpose of this vector, and after that I have multiplied with that. So this is nothing but some kind of a scalar. Okay, now you can see here that I can tell that whatever projection, okay, so projection vector is going to lie on this space B, but that is not whole space. So I can tell that, okay, this eta I can able to define, that is direction of B, but a scaled version by gamma. So this is nothing but some kind of a scaling factor. Now what I have done, I have just substituted this scaling factor. Okay, and at that time I have also substituted this result, because I know that this is orthogonal projection. So orthogonal projection eta is nothing but that is in the direction of subspace, and zeta is perpendicular to that or orthogonal to that. Due to that region this equal to 0. Okay, so that kind of result I have substituted, and eta equal to gamma b I have substituted, and after that I will get the value of gamma, that is B transpose A and B transpose B. Okay, so in two-dimensional space I can able to now calculate eta. Okay, so what now I am going to do, in place of B, now I am going to substitute the phi. Okay, and y variable I know, so I have measurement. Now what I am going to do, I am going to project my measurement. Okay, and I have to do the estimation. So what I am going to do, here you can see that projection of A on B. So what I am going to do now, I am projecting y on, and bt is what, now I have explanatory variable, so I am going to replace with explanatory variable. So you can see that it means that suppose I have some kind of output I will get, and I will create some kind of subspace with the help of explanatory variable, and after that I am going to check the orthogonal projection of that. Okay, so orthogonal projection of that is nothing but the estimated parameter. Okay, and once I know the estimated parameter, I can also able to get the estimated output, because we know that y equal to phi into nu plus e. Suppose for time being I have done the best least square estimation. It means that there is no error. Okay, so at that time what happens, that estimation of this is nothing but estimation, means if I substitute estimation of this, then y bar I will get. Okay, and you are already well aware that always there exists some kind of error, and due to that reason always in this process there exists this kind of error. Okay, and now if you calculate y bar from the least square, then again you will get same kind of result. It means that either I can go via, here I am just seeing the scalar case. If you check the vector case, at that time this is nothing but the inverse. Okay, so what we have checked, we have done that in two different way. One using least square I have generated result, another just by projection I have generated result, and finally I will get the same result. Okay, what does it mean? That the if I have some kind of least square estimation, okay, so that is nothing but one can interpret that as a orthogonal projection. Okay, so orthogonal projection y bar is the estimated output y bar, and zeta is the error. If you take this, the dot product of this equal to 0. What does it mean? That zeta span the shortest distance between y and y bar. Okay, so whenever you are doing least square estimation, at that time I have actual measurement, and now what happens, that whatever unknown we are getting, so unknown we are getting with some kind of error. Okay, so unknown corresponding to unknown I have some kind of predicted output. Okay, so this zeta is nothing but the shortest distance between actual output y and predicted y bar that we trying to minimize. Okay, so that is the interpretation of the least square estimation, because two different way I have actually generated result, and finally I will get the same result. Okay, so basically what least square estimation is doing, and finally I have also interpret like this. So since P is projection matrix, so if, and it is possible to show that P square equal to P and P transpose equal to P. Okay, so now this matrix I am telling up to here, that is P matrix, and you can check that these two result is true. So that is nothing but the orthogonal projection matrix. Okay, and this zeta is nothing but the orthogonal, again orthogonal projection. So y bar, the span of column vector of phi, and zeta are found in such a way that they become a orthogonal vector. Okay, so what I mean to say, that suppose you have some system, and what basically you are going to do, you are going to take some kind of measurement, you have some knowledge of explanatory variable, and after that you have to estimate this y, this new. Okay, so exactly you are not able to estimate. So what happens, that if you perform the least square estimation, okay, so that is nothing but whatever measurement you are getting, so unknown quantity, so y measurement I have, and based on that I have actually get new. Okay, so whatever new bar, exact new bar is not possible to get, so new cap you are getting, so that is nothing but the minimization of these two quantity. Okay, so zeta is orthogonal, so we try to minimize this y and y bar. Okay, so exactly I cannot able to fit, but approximately I can able to fit it. That is the interpretation. Okay, so least square estimation I can able to interpret in terms of the orthogonal projection. Okay, now last part is orthogonal subspace, and what we have seen, I have some kind of vector, and I want to project that vector on some kind of subspace, okay, of a inner product space. Why inner product space? Because whenever we are generating some kind of coordinate system, at that time I need some kind of norm. Okay, and norm is nothing but the that is generated from the inner product. We have just seen that suppose w is nothing but c1 u1 c2 ut2 and up to cn un, that is the orthogonal projection, and c1 c2 cn we are generating using some kind of, with if u1 is orthonormal, again I have to check that norm equal to unity. If that is orthogonal, then you have to calculate the norm of that. And due to that reason, we are assuming that now I have some kind of inner product. So I have two subspaces now. Okay, and I have to project one subspace into another subspace. So first, what we have to do, we have to check that two subspace under what condition two subspaces are orthogonal. Okay, so definition is like this: two subspace W and Z, that is subset of V, are called orthogonal if every vector in W is orthogonal to every vector in Z. Okay, so whenever you have to check the orthogonality of one vector on some subspace, then what happens, that one vector is fixed, but you have to check about the all vector of subspace. But here what happens, you have to check the orthogonality of two subspace. So now you have to check something more. Okay, because you have to check the orthogonality of two subspace. So again, same like previous. So in other word, W and Z should be 0, and for all W and all Z we have to do that. Okay, but this is not possible to do because W is some kind of subspace containing infinite number of vector, and due to that reason, now what we can do, that same like whenever I am projecting some vector or checking some vector is orthogonal to subspace, at that time we are just seeing the some kind of basis. Based on that basis, that particular orthogonal subspace is generated, and after that we are just taking the inner product with that basis vector. So here what I have to do, I have to see the basis vector of both space, and after that we have to check all combination. Okay, all possible combination, and their inner product we have to check. If that is equal to 0, then I can tell that two subspaces are orthogonal to each other. Okay, so same kind of things, whenever we are checking, we are doing same kind of things. Okay, so lemma is w1 w2 wk span w, and z1 z2 zl. Suppose I have taken two subspaces, and both subspaces has no similar dimension. They have, one subspace has k dimension, another subspace has l dimension. Okay, so at that time what we have to do, we have to see the basis, and after that I have to take the inner product of w and z I, and I have to vary I from 1 to k and j to 1 plus l. And if that equal to 0, then I can tell that two subspaces, okay, of some vector space are orthogonal to each other. Okay, now I have generated one example. So I have taken three-dimensional vector space. Okay, and obviously I need the notion of some kind of inner product, so I am taking inner product as a standard dot product. Okay, now what I am going to do, I am going to take some kind of plane in three-dimensional space. Okay, so this is nothing but some kind of subspace. Now what I am going to do, that I am going to check that this particular plane, okay, is orthogonal to which plane. Okay, so again, that is nothing but I have to generate some kind of subspace. Okay, and it is possible to show that if you take any w x y z that belongs to w, then this kind of condition is satisfied: 2xy plus 3z equal to 0. Okay, and in this way one can tell that, okay, if you have this kind of plane, so I can again generate some kind of plane, okay, which is orthogonal to each other. Okay, in this way I can able to talk about the orthogonality of two space. Here again, next example, suppose if you have w is a span of these two vectors, okay, and z is the span of these two vectors, and in order to check that these two subspace, and here you can see that this is fourth dimensional vector space, because I have four number of component inside w1, so I have four dimensional vector space, and inside that four dimensional vector space I have created some kind of subspace which is spanned by these two vector w and w2, and z is spanned by z1 and z2. Now we have to check that these two subspace are orthogonal to each other or not. So how to check that orthogonality? Again, I have to fix the some kind of dot product, okay, some kind of inner product, and I have selected inner product as a dot product, and it is possible to show that if I take a standard dot product at that time, w1 z1, w2 z2, w2 z1, w2 z2, means I have checked for all possible combination, and this equal to 0. So I can tell that w and z, that is subspace of fourth dimensional space R4, that is under the Euclidean dot product, that is perpendicular. It might possible if you change the dot product, then these two things are not orthogonal. So please be careful. Okay, so you have to specify that which kind of inner product you are considering, and what kind of space you have, and what kind of subspace are actually perpendicular, what kind of those two subspaces of main vector space R4 are perpendicular. Okay, now another definition, that is orthogonal complement of a subspace W that is subset of V. Okay, so what we are telling, that orthogonal complement of a subspace W, that subset of V is denoted by this symbol W. Orthogonal is defined as the set of all vector which is orthogonal to W. Okay, so whenever we are talking about W orthogonal, at that time I have to select all vector V, which and I have to make sure, since I am checking that whatever orthogonal complement. So orthogonal complement, in order to check the orthogonal complement, I have to check that all vector of this subspace W and this vector V is actually perpendicular to each other, means inner product equal to 0. Okay, now what I have done, I have, for example, I have actually telling that I have some kind of W is subspace in three-dimensional space, and T I can vary any real number, and in this way I can actually generate one-dimensional subspace in three-dimensional space. And here you can see that I have some kind of vector W1 2 3 in R3, so I have selected the basis. Okay, now what I have to do, I have to talk about orthogonal complement. Okay, so how to talk about orthogonal complement? I have to identify all vector which is perpendicular to this. Okay, so now basically I have to solve this z into w that equal to 0. Okay, so this equation I have to solve, homogeneous linear equation I have to solve. So you can see that I have three unknowns inside this equation. So if I fix two unknown, then I can able to comment about the two unknown, then I can able to identify the one dependent unknown based on two. So what I have done, I am assuming y and z is known to me, so I can able to fix the x, and in this way I can able to generate that kind of complement space. So complement space is nothing but like this, and here z1 and z2 is the indicated basis, and that is obviously that is not orthogonal, and y and z you can take the any vector. Okay, so in this way you are able to generate, suppose if you have some kind of subspace and if you want to generate the orthogonal complement, then in this way you are able to generate. Okay, just by definition. So now what next proposition is telling, next proposition is telling that suppose W is subset of V, is a finite dimensional subspace of inner product, you can fix any inner product, then every vector V can be uniquely decomposed by these two. So one vector on this subspace and another vector Z, that is the actually orthogonal, here orthogonal to this space. Okay, so any vector of this V you can able to decompose as a subspace and they are orthogonal vector. Okay, so same kind of things actually one can see just by the definition. Let W belongs to big W be orthogonal projection of V onto to W. So by definition we have already seen. So from this definition you can see that V is nothing but Z plus W. Okay, and Z is nothing but the perpendicular to the W. Okay, and due to that reason means I can able to write about this result, and it is possible to show that that is also unique. And how to prove uniqueness? You can take vector and you can express that is w plus z, and you can tell that okay, apart from this I have another decomposition, that is w cap and z cap. Okay, and after that you can just rearrange it, because v I can represent like this and v I can represent like this. So if I subtract, then this kind of relation comes into picture, and it is possible to show now the left hand side of equation lie on w, while right hand side actually lie on w perpendicular, because z on the perpendicular direction, and we have already seen that both are the orthogonal to each other, and due to that reason means only one vector belongs, common vector belongs to both, that is 0. So it is possible to show that this actually decomposition is also unique. Okay, so what last result is telling, suppose you have some kind of subspace of vector space, so it is possible to express any vector in terms of that subspace, and after that they are orthogonal projection. Okay, so in this way one can do. So now it is time to conclude the today's lecture. So what we have seen in today's lecture, so we have developed basically two different concepts. So I have some kind of vector and I want to project that vector on some subspace. Okay, so how to do that projection? And so for that we have means develop some kind of definition, and after that we have, using the help of orthogonal and orthonormal basis, we have able to generate that particular orthogonal vector. Okay, and after that we have interpret the least square estimation, and then in last part we have discussed, if we have two subspace, then how to talk about orthogonality of those two subspaces. Okay, so this, with this remark, lecture is now in from my side. If you have any specific question, then please let me know. So orthogonality part is now complete. Okay, so thank you very much.